All right, well, welcome everyone to Jason Wu's Defense. I'm Jeff Bigham from the HCI, and it's my great pleasure to introduce Jason. So it's been almost 6 years that we've worked together, and I'm just really excited about the work that he's going to present today. I think it's really important. So we every day use user interfaces, graphic user interfaces, and yet we have very little ability to really reason about them. We don't really have ways for computers to understand them very well, and Jason's work has kind of directly over a series of projects kind of addressed this. And I think it's become even more important as people have thought about all the exciting ways that the new generation of AI is going to be able to work over, automate, help us with tasks that we perform on user interfaces. And if we can't actually access what those interfaces are about or what they can do, then we have a much less ability to be able to make those things work. And so I think it's a really exciting set of work that he'll talk about. I want to very briefly introduce committee. So right in front of me, we have Jody Felizi, Jeff Nichols. Oh yeah, we can, yeah, clap, yeah. Go Jeff Nichols. Yeah, okay. And then on the internet, we have Sherry Wu from the HCI and LTI, who's joining us, I believe from China, so it's late, so you have to be quick before Sherry reasonably falls asleep.
I'll try.
Or just really exciting. And then also Tom Mitchell, who's joining us, I think from California. And
only in California.
Right. Only in California. And so this is the committee. So what we'll do is Jason will speak, and then we'll have a round of questions from the committee. Usually we go furthest away to nearest. Jason will defend with those questions. And then we'll open it up to the audience, and then I think maybe we'll go another round, and I kind of forget what happens then. And then we'll kick everyone out. We'll deliberate, and then we'll probably sign this paper, and we'll all celebrate. Okay. But without further ado, Jason, take it away.
Yeah, great. The other important news is that there's some breakfast at the back. Okay, so yeah, great. Today I'm really excited to be here to talk about this research I've been doing in my PhD that I call computational understanding of user interfaces. And it's kind of like Jeff said, I'm really excited to talk about how I think computational methods like data-driven machine learning have this huge potential to address some of the core challenges in human-computer interaction and some of the work that I've done to show that. So I want to start by sort of imagining the future of computing, right? What are computers going to look like in the future, and how are we going to interact with them? And right now is such an exciting time to be thinking about this question, right? There's so many visions imagining how computers can augment reality, how they can respond naturally to our queries, and even how they understand some more implicit interactions like movements and gestures. And the key promise here is by doing this, we want computers to be more natural to use. They're going to be more personalized. They're going to be more adaptable, more context aware. And this is going to allow all of us to flexibly interact with digital information, whoever we are or wherever we are. But if we look at user interfaces today, we have to realize that they're not quite ready yet. And a lot of the functionality that we use computers for are actually locked behind UIs built for a relatively rigid set of assumptions. So like, for example, a lot of them are designed to only run on one specific kind of device and pre-programmed for that specific layout. And UIs also make a lot of assumptions about users. So because of this, a lot of non-experts would find applications hard to use or hard to learn. And what if the user is blind and can't see the screen or has some other accessibility needs? And even when we've developed other programs like assistive technology and development tools to help address these problems, we find that they often don't work when these UIs are missing the needed APIs and toolkit support. And these are just a few of the examples of assumptions that are baked into UIs today and how they limit how we can use computers. So a grand challenge in the field of human-computer interaction is actually overcoming these challenges, right? And answering this question, how do we make computer interfaces useful for all people and across all contexts? And one reason this is hard is because today most UIs are first manually designed, and then once they're compiled into an application, there's not really a good way for us to dynamically change them after that. And so the main goal of my work is to overcome this by building machines and computational systems that understand and operate maybe an existing UI, and then use that understanding to create something more usable and more accessible. So just imagine, like, what if assistive technology could work for any UI, where, you know, a blind person could maybe point a smartphone at an interface and receive natural language description and usage guidance, which is effectively a new sort of interface. Or maybe imagine a machine that can use inferred knowledge of user goals and distill down a complex piece of existing software into an easier to use version. Or what if a machine could interact with the 2D WIMP interface and maybe translate that into an entirely new domain, like augmented reality and a new set of interactions that come with that. So by computationally understanding their functionality and content, we go from creating UIs as a static piece of output and transforming it into a malleable representation that can be reshaped for new devices, modalities, and users. So in my talk today, I'm going to share my work that has started to build the technical foundation for this vision. And I'm going to talk about specifically 3 different areas that I see that make up this foundation. So first, I'm going to talk about user understanding. How can machines understand user needs and context, which HCI tells us is the basis for building a good interface? And ideally, we could do this automatically by implicitly learning it from usage behavior and interactions. And another question is, how can machines reliably understand existing UIs? Most current approaches, they require access to source code or some other underlying representation in order to work. So we want to build a machine that can use a UI, any UI like a human can, using the same kind of default input and output modalities, and really understand what it's trying to do. And then finally, I'll talk about how we can combine some of that user and UI understanding together to generate optimized and more personalized interfaces. So to describe my research, I'll first talk about this problem of user understanding, right? So how can machines understand user needs and the context in which computers are used? And a really natural place to start when thinking about this bigger idea of personalization is the existing settings and features that already exist on a lot of consumer devices. So there are these settings, especially accessibility related ones, that can let you change how content is displayed, change how you interact with apps, and even let you use alternative modalities like gestures and voice. And in fact, like I said, there are dozens of these pre-installed already on a lot of consumer devices, like the iPhone, that, you know, represent decades of progress in assistive technology and personalization. And so in this project, I was interested in understanding, well, how are people using these features, or if they're actually even aware of them at all. Okay, so I conducted this survey asking 100 online respondents about what certain features do. And unfortunately, what we found was that awareness of these features was really low. So the chart here shows the percentage of respondents who knew about some really basic features. And awareness was, especially low for people like older adults who are likely to benefit from them and develop accessibility needs as they age. But yeah, they don't know about them or how to use them. And so to give you an idea, just less than 20% of respondents here even knew what the term accessibility means in the context of their settings. So a classic approach, if you will, to solving this is building a recommendation system. That essentially might recommend features to people who don't know about them, but could be who could find them useful. And the main idea behind popular methods like collaborative filtering is that if we group together similar users or similar items, we can use that to infer things or features that a new user would probably like. So that's how a lot of recommendation systems work. But one of the problems here is that because awareness is so low, very few people have anything enabled, right? So in recommendation systems, this is called the cold start problem. And so the question becomes, well, how can we bootstrap this? There's been some other related approaches out there where a user could play a game or complete some kind of wizard that predicts some relevant settings to start out with. But the user would also need to know that they should actually start that screening app in the first place. So we decided that it needs to be really proactive and automatic in order to be effective. So to augment that standard strategy of recommending similar items, which we call grouping here, we developed a couple of interaction-based strategies for recommendation. So, and we also chose recommendation instead of just silently enabling features, because not only can we get over this cold start problem, we can also begin to educate users and people about accessibility. So one strategy we looked at involved extracting statistical features from streams of sensor data that could tell us about what the user is doing or how they're physically holding or manipulating the device. Another strategy focused on usage sequences. So we can look at interactions and see, for example, if the user took a picture of something and then immediately opened it up to try and zoom in to see something more clearly. And then finally, there was a variation of this that focused more specifically on certain types of errors and used that to infer what the user was trying to accomplish. So I'll show examples of these in a second, but the point here is by bringing together all this information from natural interaction, we can get this picture of user ability and needs. So here's an example that uses a statistical detector on sensor data. So if the user is always holding the phone really close to their face, we can measure that with a depth camera and infer that they might benefit from zoom-related display features and service that in all these different ways, like a notification or a home screen widget. And here's another one for a feature that adjusted a threshold for the double-click speed of the side button. We can detect what we call near miss errors. So if a failure occurred because the double click was slightly slower than the default threshold, then we can use that to recommend, slightly slower threshold that would be better for the user. So for this system, I ran a user study with 20 older adults, and we collected feedback on how we should surface these recommendations and also tried to measure the system's accuracy. And from a relatively short usage period of performing everyday tasks like watching videos and web browsing, our system could generate recommendations that were usually seen as helpful. And so this is a promising way, this suggests that this is a promising way of using usage interactions to understand computing needs and then mapping them to existing features that can address them. But there's also a problem with this approach of adaptation, and that sometimes, even when the correct features are enabled, they don't work because there are a lot of applications that don't support them properly. And to illustrate that, let me show you one example of a feature called a screen reader. So a screen reader is a program that allows someone who's blind to access graphical user interfaces by cycling through the elements and giving a verbal description.
Start accessibility by starting. Thesis. At accessible name. I stepped out of my screen. 48 meters 9/15/1 bullet 9:58 a.m.
So what's happening here is that it kind of read out like one of the elements, it described it, and then for text elements, it would actually read the content of the text. But for some apps, some other apps, it, for that app it worked, but for some other apps it won't. It'll actually miss most or all of the important information. So here's an example where it doesn't work, and we can see what happens instead. It wasn't able to read, properly describe the screen. So what's going on here? It turns out in order for these features to work, they don't really see UIs the same way that humans do. They have to rely on a special type of metadata or some sort of developer-defined API in order for the feature to know what's on the UI and actually how to operate it, how to interact with it. But in our work and what's been documented by other previous research, we found that a lot of apps don't include this metadata. And this is because they're built with inaccessible toolkits like game engines that actually don't generate this metadata properly, and also low developer awareness and unwillingness to put in that extra necessary implementation effort. And it's not just the accessibility features that suffer from this. So much of the infrastructure that we currently use to automate or programmatically interact with UIs is actually built on the same metadata. So these are things like UI testing frameworks, automation for virtual assistants, and even some of the newer LLM-driven agents. In order to work well, they all assume that there's some kind of API available, or you would need to feed in, for example, the DOM or a source code of like a web page. So this brings me to the next part of my talk, which is about UI understanding. How can we get machines to reliably understand and operate user interfaces? Because if we can do this well, we can enable all of that current infrastructure to work into many cases where they currently don't. And we can also unlock new opportunities for future applications. So there's a lot that we need to know about UIs in order to use them. And the interesting and a little bit of an ironic thing is that on the creation side, we've made so much progress in terms of how we build these user interfaces. We've went from basically manually positioning widgets at fixed coordinates on a canvas to really interesting constraint-based layout solvers that can really handle more responsive layouts. And what we're starting to see now are these declarative UI libraries that really tie together the appearance of a user interface and the underlying semantic content and functionality. But on the consumption side, somewhat unfortunately, all of that abstraction is hidden away from us. And they're locked behind pixels if we don't rely on this additional metadata, which again is often missing or incomplete. So how do we take those pixels and then extract all of that useful stuff that we need back out? And this is a challenging problem, right? For example, to recover the content presented, we have to reason about all the different modalities of the information and content that is in the user interface. And depending on the task, you might also need to go deeper and understand really the relationship between different items and even the functionality of the screen, like what can I actually accomplish with this user interface? So the first thing we looked at was this problem of the screen reader that I just showed you. And in this project called Screen Recognition that I worked on, we addressed this problem by building a computer vision module for detecting 12 different types of UI widgets from screenshots of applications. And there were a couple of steps to implement this system. So to train this element detection model, we had annotators install 4,200 iOS apps to capture and label screenshots of user interfaces that occurred in those apps. And this led to a data set of around 80,000 screenshots labeled with those 12 widget classes where they appear in those screenshots. And then afterwards, we use this data set to train an efficient single shot detector that could efficiently run on a mobile device. And then we applied some model post-processing and actually integrated this model into a screen reader called VoiceOver. So to give you an idea, this is what that same previously inaccessible app that I showed you sounds like now using this system.
The achievements button. Shot. View our 5W go.
So it was basically able to read some of those text, some of those UI elements where previously everything was unavailable. So this approach was quite successful, and we performed both a metric-based evaluation and a user study. And using standard metrics like mean average precision, we found that our model could pretty reliably detect these on-screen widgets. And when we ran a user study with 9 screen reader users, we found that they were able to use 22 apps that they chose that were previously partially or completely inaccessible. They were able to use it with this new system. So that really improved usability. And finally, what was really great was that this project was released as a feature in iOS 14. So hundreds of millions of users can actually benefit from this technology and use all sorts of new apps. And the development of screen recognition and feedback from users led to a lot of follow-up work here. So for example, it turns out that icons are a really hard kind of sub-problem because different apps use different icon sets to describe that same concept. And there's this huge long tail distribution of icons outside of those like 12 predefined classes that we decided on. But those are nevertheless very important for less popular apps that people need to use. So I worked on this project where I applied few shot learning techniques that allows users to actually dynamically register new classes of icons that they're interested in. Another thing I did was to really scale up this process using web data. So compared to, if you think about other data sets like ImageNet, which is a couple of million images, or the trillions of tokens used for the latest language models, we realized how limited user interface data is. So in this project called Web UI, I developed a system that crawls web pages and will take screenshots of those web pages and then train a model to associate that visual appearance with some extracted metadata that will tell you where elements are in the styles. And I use this data in a lot of different ways, and including transfer learning, semi-supervised learning, and domain adaptation that really improved the performance of the model that I showed you. And we've also publicly released a data set and models from this project. But all of that work is actually just a subset of that metadata that called the view hierarchy object and those semantics that we want to extract from a user interface. And some of those downstream applications I told you about generally rely on more than just a list of bounding boxes that you get from an object detection model. Even in the case of a screen reader, a list of bounding boxes really isn't enough information, because you actually have to compute the right order to read out and describe those elements. And if you did like a simple rule, top down, left to right, you would end up with a really confusing description for things like the bottom toolbar, where you would essentially first describe all of the toolbar icons, and you would kind of circle back and describe all of the labels. So that would be very confusing. So part of the post-processing that we originally did was writing a bunch of manual heuristics that tried to handle common cases, like grouping pictures together, but this wasn't really a general solution to this problem. So in this project, screen parsing, I defined this problem that takes in that same screenshot and not only predicts a list of elements, but also uses them to build this hierarchy, this multi-level tree that represents a lot more UI abstractions. And to do this, we developed what's called a transition-based parsing model that we called a screen parser. And I'll give you a very quick overview of how this works. So first we use an object detector to segment the screenshot into different widgets, which is essentially what screen recognition did. And then we fed this into a parsing network. So the first stage of this parser is a type of what's called a recurrent neural network that encodes this flattened list of UI detections. And then the output is also, of this stage, is also an embedding for each detected UI element, and also a hidden vector called H that describes kind of the structure of the whole sequence it's seen so far. And unlike a lot of models that directly predict a single fixed output, our model needs to predict this variable size tree, which can vary depending on the input user interface. And it does this by producing a sequence of nodes and actions that describe the correct hierarchy. Sort of if you think about, sort of like how if you think about depth first traversals of a tree, you can look at the nodes and stack operations and kind of use that to infer what the tree originally looks like. And so our parser essentially does this traversal in reverse with the help of a stack data structure. And so at the beginning of decoding, we have a stack populated with only this single root node, which corresponds to this intermediate tree here. And to grow this tree, this model essentially continues to evaluate this equation that looks at the current hidden state and tries to predict the most likely node to attach onto this tree. So it's essentially gradually growing it using the correct, based on the correct structure. And so this network can kind of attach one of those detections that was detected by the object detector, or it can create a new node that represents some sort of like intermediate container object, like a list or like a grid or something, and add that to the tree. And then finally, there's this special pop action that will kind of let you let the model essentially move to different parts of the tree. to describe its structure. So this process is repeated, and essentially the stopping condition is when, all of those input elements have been added to the tree. And we use a separate classification model to try and predict, to give us some more information about the intermediate container types, like if this container was like a special kind of list or special kind of grouping that would be helpful. So the overall result of this pipeline, to summarize, is that just from a screenshot, we can kind of reverse engineer this view hierarchy artifact, which enables so many of the other things that I talked about. Going back to the computing the reading order of elements for screen readers, we now have this data-driven model that can cover a lot more cases than just those manual heuristics that we use. And this also means that for other downstream applications I talked about, they can also potentially work as well, because they couldn't work with only the listed bounding boxes. And one example that kind of really shows how this output captures important information is this UI retargeting application. So we applied this technique used in compilers and code generation called the visitor pattern to try and map nodes in this hierarchy that we predicted about a screen, and we can map that back into code snippets that will that you can run to kind of reconstruct the UI. So it really just shows you the information it captures is kind of sufficient for also reconstructing the original UI to some extent. So in addition to these applications, we also performed this quantitative evaluation with iOS and Android screenshots, which we found led to significantly more accurate predictions for both lower level groupings and also the overall structure compared to those original heuristics. So screen parsing here, it showed it's possible in many cases to, again, reverse engineer this metadata, the view hierarchy, using machine learning. And that's indeed what most existing infrastructure relies on. But how do we go beyond that and really enable machines to actually use UIs in order to accomplish tasks? And to understand a UI's functionality, we need to build a model that sort of recognizes its affordances, which are basically things and tasks that you can do with the UI. And at first glance, this seems pretty similar to a lot of the other things that we did, but it turns out it's harder. So we initially tried to just ask annotators to essentially identify how UIs could be used by drawing boxes around buttons that are clickable or things that you can swipe on. But when we try to do this, even for tasks like simple, what we call tappability, like if you can actually tap on a button, this led to really poor performance, and a lot of the labels that annotators gave were actually wrong. And this might make a little bit more sense with an example. So if I showed you these screenshots of apps, you might be able to kind of look at it and identify, some of the interactive widgets that you can tap on. But it's really easy to miss others if you don't really have a chance to play around with the app. And that's how we as human users usually go about learning how to use apps that we're not familiar with. We don't really look at a lot of pre-labeled examples, right? And based on this intuition, we developed several strategies to sort of infer UI semantics from interactions rather than these annotations, which we previously used. So for example, if we want to know something is tappable, we can get the system to actually tap on an element and sort of observe if it arrives at a new screen or if there's some other kind of visual effects that stem from it. And we can also do a similar thing for draggability. And essentially what we expect is if something is draggable, it would follow sort of a virtual finger across the screen as we move it around. And based on this idea, we built this app crawler called the Never-Ending UI Learner. And you can see here it's crawling and basically training itself through its own interactions. And this took a significant amount of engineering effort, but it allowed us to apply this approach to 6,000 real apps from the iOS App Store. And this system called for, I think, a total of 5,000 device hours. So it allowed a lot of this like model learning to take place. And from this footage, you can see that, not only is it attempting to tap and scroll to learn what individual widgets do, it's also able to kind of discover entirely new UI screens that it's able to learn from in the process. So from these interactions, the crawler, continually trains a set of models that it uses to perform its crawling. And, although this technique could be applied to any kind of model architecture, in our case, we designed this novel multi-headed architecture that allowed it to be more efficient and stable. And it does this essentially by sharing the representations between these different affordance predictions models and only training a subset of the most important parameters. We conducted a quantitative evaluation where we asked a lot of human annotators to annotate actually the videos recorded from the crawler's interactions as ground truth. And at a high level, we found that this agent could successfully learn the semantics for these different interaction affordances much more accurately than is possible through just human labeling. And not only that, it improved itself over time and can automatically handle things like new updates of apps. So I think this is a really positive result that shows that machines can both use and also learn to use UIs more like humans do. So now that we have a computational representation of the user and the computer interface, I'll talk about how we can kind of combine these two together to actually generate more optimized user interfaces. And one application where this could be really useful is called ability-based design or ability-based adaptation. And this essentially describes methods to tailor UIs to user ability or certain situational impairments. And this idea was actually introduced to the HCI and accessibility community many years ago, but it never really gained widespread industry adoption, I think, in part to the high cost and effort of getting developers to actually implement these adaptations. So I wanted to apply these principles to existing apps at runtime in a way that wouldn't require any extra changes. And since we have extracted representations of the user and also the UI that we can easily manipulate, sort of a natural option to think about is optimization, which would allow us to modify those representations to try and maximize some sort of objective. And so I built this system called Reflow that allows you to plug in, a UI understanding model, in this case, an element detector, and combine that with a personalized model of a user in this pipeline. And, together what would happen is it would optimize that layout and then try and re-render the UI for that user using some computer graphics techniques. So to model usability, we used our representation called a difficulty map, which you can kind of think of as a spatial representation of which parts of the screen are harder to tap or interact with. And you can compute this using a variety of methods, like the error detection strategy that I described earlier. But for this project, what we did was we just had users perform this calibration task that required them to quickly tap on different parts of the screen. And using this personalized map and a UI layout, we can kind of score a user interface by adding together or integrating the amount of difficulty contained within its elements and then summing that up. And we took this calibration data, this user calibration data, and trained this surrogate model that allowed us to more efficiently estimate this score rapidly and use it as an objective function for an optimizer that can modify the UI. We use this approach to make small modifications called refinements to existing app layouts. And when we conducted a user study with 10 participants, where each of them performed this calibration task to generate like a personalized map, we found that this led to, on average, 9% faster completion time when they were using, compared to when they were using the original app layouts. So in this sense, you could say that the optimizer succeeded in meeting its objective, because in each each user's difficulty map, we can see in like the red kind of difficult areas, elements got larger or they got moved away. But this figure also shows the limitations of the approach. Because simultaneously, you can see that the optimizer also introduced some design defects by violating constraints like alignment and consistency. And a part of this limitation is due to the optimization method itself. We tried other approaches to try and essentially predict those constraints and also introduce them into the optimization process. But it gets a lot more difficult for an optimizer to solve all those constraints the more that you have. But I think a more fundamental part of this is that objective didn't really capture everything that's important. And it's the same even for more recent large language models and other approaches where the models have been scaled up with massively, larger size and more data, but hasn't really captured all of the important aspects of a good design. So to address this, I worked on a project with LLMs, and one of the motivations was to actually generate the code for a UI instead of directly predicting the layout. Because if you run code through a UI toolkit, then the rendering engine, like the toolkit, can actually handle a lot of the problems related to alignment and consistency. But it also introduces new challenges, right? Because this model now needs to understand the syntax of UI code and actually also reliably generate compilable programs, and also kind of understand from a perspective of generating code what is going to lead to visually appealing or a good design. And from our own tests and other published research, we know that these remain challenging problems, especially for open source large language models. So before I get into how I address them, I'm going to give a really brief overview of how LLMs today are usually trained. So they're usually trained in multiple stages. And in the first, the majority of the training time is spent doing what's called unsupervised language modeling. And this by predicting sort of like the next word or token in a sequence, it allows the model to encode knowledge into its weights and learn the distribution of text and code. And then there's this second stage called supervised fine-tuning, where we take some examples of input and output pairs and use that to teach the model to follow certain imperative instructions that a user can give, and also how to format its output. And then finally, during the alignment stage, we have this separate what's called a reward model or some preference rankings that can further guide the model to generate higher quality responses. And this pipeline requires a huge amount of data and also a lot of human annotation in the later stages. And I would say that applying it to user interface code is particularly difficult, right? Because a lot of the code data sets crawled from the internet, they're not really self-contained code, or you can't just like take it and directly compile it. And you would also need programmers, a lot of programmers to write the human written example code, and a lot of designers to rate the quality of the resulting UIs. So a lot of the existing work on code generation here essentially trains on the output of some existing, strong proprietary model. And this is a process called distillation. But the proprietary models themselves, well, it's not really known for sure, but it's really likely that they're trained with actually thousands of contractors. This is a news article talking about what OpenAI is, rumored to be doing. So the focus of our work called UI Coder is to try and incorporate automated feedback from tools during the training process to try and improve itself instead. We know some of the properties of UI programs that we want, like they should be syntactically correct, and they should also have visually relevant designs. And so we design success criteria based on the output of automated tools such as a code compiler and a vision language model called CLIP that allows us to kind of score the visual relevance of an original input prompt and how the rendered UI appears. And we incorporated these success criteria to fine-tune an open source LLM called StarChat Beta. And our method was based on a technique called rejection sampling. So we use this original base LLM to generate a large amount of output, in this case, 100,000 Swift UI programs. And using our code compiler, we can first filter out all the programs that didn't compile. It actually only led to 10% of those left. And while you can see while these programs are syntactically correct, you can see like the designs are very simple and they're not really good. It's not really clear what those UIs are even supposed to be used for. But then we can also apply our vision language models success criteria to kind of compare the rendered screenshot with what it was originally prompted to do. And using this, we can further filter down this data into 400 examples that have sort of the best matches between the description and the rendered screenshots. And if you and we repeated this self-training process for a total of 5 iterations, and we found that it led to significant improvements in this language syntax understanding and also design quality. So for example, the final compilation rate went from, only from 10% to around 80%, to give you an idea. So we ran this sort of arena style evaluation with human judges and a set of baselines where essentially, a judge was randomly shown output from different models and they were asked to choose the better one. So this, a model does better if it's expected to, be chosen over other models with a higher probability. And what we found was that UI Coder significantly outperformed all the other downloadable models, including much larger ones, distilled from GPT-4. So this UI Coder model that we developed also started to approach the performance of the proprietary models themselves, which are, estimated to be much larger and trained with a lot more data. But despite the relative performance and level improvement, I think there's still a really long way to go in terms of absolute performance, right? So for example, we can see that here UI Coder makes a lot of poor design choices in terms of things like formatting and also style choices, right? So why is that? Especially since we used another model to try and score and filter the output for design quality. Well, a natural thing to look into is to try and find out if, machine learning models like the one we used for this task called CLIP can actually do a good job of assessing UI design quality. And to do this, I first ran a very simple experiment. I first manually wrote some code to implement the simple shopping app. And since I have the code for that app, I tweaked it to intentionally kind of create several suboptimal versions. So here's one with, a poor contrasting background that makes it harder to read text. Or I can introduce other defects where I've made the text size so big that it begins to kind of overflow. Or I can even start to mix these two together. So I can, generate a lot of these suboptimal variations. And then we can take the original user interface and this suboptimal version and check to see if various ML models out there can actually identify which of these screenshots includes these design defects. And for this illustration, I'm prompting GPT-4V using a well-known set of visual design guidelines and asking it to choose out of those two screenshots there, which one is better designed and explain why. And I've also tried this with the CLIP model that I used in UI Coder with similar results. And what we see is that, GPT-4 and other models, they don't really do a good job of this. So here it states that the screenshot on the left is, better designed, and kind of the reasons it gives aren't really correct either. So it says that, I think it said it was more consistent and better aligned. So that's why it thinks the one on the left is better, which is, I don't think, true, by the way. So the short answer to this question of can current ML models accurately assess UI design is no. Among the models we tried in this comparison task, pretty much all of them got around 50% accuracy, which is basically like flipping a coin because there's only two possibilities. And it's actually a little bit worse than that because we found that GPT-4 at least really likes choosing whatever screenshot is on the left. So even if you shuffle it, it'll like pretty much always say the one on the left is better. And the reasoning it gave is also often incorrect. It contained a lot of hallucinated details. It's also unable to understand sort of the trade-offs between different design guidelines, right? So one thing you might want to do is have bigger text for readability, but you also care about things like contrast, which might require some text to be smaller than others for emphasis purposes. So the model is not really able to evaluate that well. So how do we fix this problem? Well, to get a model to learn, what a good design is, we need the right data, which would ideally, I think, here consist of UIs kind of ranked by quality in terms of like pairs of good and bad user interfaces. So we came up with two different ways to get this. One way is to sort of reuse the procedure from that experiment I described earlier to sort of synthetically generate a data set. And so we built this web crawler that will first essentially visit a web page and take a screenshot of how it looked originally. And then we have, it runs some JavaScript code dynamically that we call jitter functions that will randomly inject different design defects based on a set of design guidelines, and then take screenshots after that. So now we have sort of like a quote unquote original good UI paired with a bunch of suboptimal UIs, or at least ones that are sort of worse than that original UI. And using this approach, we generated and ranked 2.3 million examples. But of course, good design isn't only about avoiding like design defects. So we also collected some feedback on a smaller set of 1,200 real world app screens ranked by human designers. And one important difference here is that these screenshots don't necessarily contain a design defect that was intentionally introduced, right? So they're more reflective of subjective preferences. We tried two different ways to use this data to train our model, which in our case, we tried to fine tune clip, which was used in our UI coder project. And we called this new model UI clip. And one way is to use what's called the clip objective. And the basic idea here is for the model to learn to associate sort of good UIs with a piece of text containing the word like good design, the phrase good design, and associate, unpreferred or worse UIs with a piece of like a description containing the piece of text poor design, and optionally a description of why the UI was rated poorly. And another method is called, we call it the pairwise objective. So this essentially focuses on making the score of the higher rated UIs greater than the lower ranked or jittered ones, and we're able to optimize for that. So how well does it work? To find out, we ran an evaluation to try and predict the presence of design defects on a held out set of those synthetically jittered UIs, and also predict designer preferences in a held out set of designer rated screens. And we can see the results of our model and also a bunch of baselines summarized in this figure. So from the previous experiment, we know that the problem of assessing UI design is challenging, even for today's largest proprietary LLMs. And this is the same is true also for a lot of open source alternatives that we tried, which are also publicly available for testing. And we did some ablation analysis that shows that, even if you used sort of existing data sets of user interfaces and descriptions to fine tune models, that's actually not sufficient to learn sort of relative design assessment, because they lack those labels for what constitutes bad and kind of better design. And finally, variations of our model here shown in a little bit of bolder text are shown to be significantly more accurate in detecting the presence of design defects, and also more accurate in predicting subjective rankings of real-world apps made by those human raters. So in this section, I've shown 3 examples of how we can, take these HCI and UI concepts and try and encode them into quantifiable objectives for generation. So first, I showed how reflow tries to quantify usage difficulty and uses that to improve target acquisition in a set of existing applications. In UI Coder, I showed how the quality of UI programs can be estimated using automated tools like compilers and off-the-shelf vision language models. And this is useful for guiding the model to generate better UI programs over time. And finally, in UI clip, I showed that the quality of UI programs can be estimated. In UI clip, I showed that we're able to further fine-tune that vision language model to more accurately assess UI designs in this data-driven way. Okay, so this concludes the work I've done over the course of my PhD that tries to address these three areas. And as a brief summary, I described several of my projects. First, I described this recommender system for inferring user context and needs from natural interactions and tries to map them to useful accessibility features. Next, I developed several models and systems that use the state-of-the-art in CV and NLP to understand and operate UIs as humans would. And then finally, I introduced new data-driven approaches to try and quantify objectives for generating personalized and higher quality user interfaces. So to wrap things up, I want to come back to this question of, how can we make computers more useful? And I said this was sort of the grand challenge in HCI that has driven a lot of the research that I showed today. So what kind of conclusions can we draw from my work? Well, I hope I've convinced you that computational UI understanding allows UIs to be dynamically reshaped in all these different ways to better fit their usage contexts. And through all of the models, systems, and prototypes I've shown, these are sort of like the different complementary possible avenues for achieving this. So these include the needs of understanding needs of users and the usage context from, again, the natural interactions that people have, understanding the content and functionality of existing UIs, which allows them to sort of be decoupled that allows content and functionality to sort of be decoupled from that original form. And again, incorporating this user and UI understanding together with models of design quality that allows us to synthesize new, more optimized interfaces for users. So in future work, what I'd like to do is, not only improve individual components of this current framework, but also look into ways of applying it more broadly throughout the entire development process. So my work here tries to make a lot of these adaptations automatically without any additional human input. But I think it would be really impactful to have these tools as design aids or testing tools in other parts of the design process. And I've actually begun to explore some of these areas and projects that I couldn't quite fit into this presentation, but I think there's definitely still a lot more to do here. And so with that, I'd like to, acknowledge some of the support that I've gotten, which has made it possible for me to get this far and almost finishing my PhD. So first of all, I'd like to thank my advisors, the Jeffs, who both traveled across the country yesterday / possibly early morning today to come to this talk, and they've supported me so much throughout my whole PhD. Jeff Bigham has given me a lot of great advice. I think probably the one I remember most was basically his suggestion for me to be more deliberate on what I work for, on what I work on, and make sure I'm answering important questions. That might sound obvious to you, but evidently it wasn't obvious to me a couple of years ago. Jeff Nichols also did his PhD here at CMU on automatically generating high quality user interfaces. So you can imagine the amount of useful advice he was able to give me there. Of course, I'd like to acknowledge all my committee members, some of whom are joining again from very far away locations. They've given me really insightful feedback on first my proposal, which was actually not that long ago, but also on my whole line of research and pushing me to frame it more cohesively and impactfully to things. Another person who traveled very far away to attend today is my partner, Shirley, who's given me so much love and personal support. And I'm trying my best to repay it slowly by being a participant in her research studies. So if I'm wearing like any jewelry, then that's probably. And next I'd like to acknowledge my lab mates in the big lab. it's surprisingly hard to get a complete, photo containing all the members. But, not only from their research support, but also their friendship from them has really been unparalleled. And finally, I want to thank all of my research collaborators and friends, which consists of the cohort of 2018, the squad in 407 Craig Street, the whole HCI family, intern buddies, and everyone else. Thank you all so much. And with that, I'd like to thank everyone for listening, and I'm happy to answer any questions.